Thank you for coming out to the inaugural lecture of the Quantum Sensing and Information Processing Lecture Series. This lecture series is sponsored by engineering and being executed through the Center for Advanced Signal and Image Sciences. Always important to get your sponsor information out there right away. So as you can see, we have a lot of lecture topics that we'll be covering, basically broken down into two parts, the first of which is quantum devices, how they work, how you build one, how to control them, error modeling. And the second part of the series has to do with applications, including quantum sensing, quantum computing, and quantum communications. These lectures are going to be spread over from now until roughly September. We're planning on having 2 lectures per month, roughly spaced a week, 2 weeks apart. So our schedule, again, approximately 2 lectures per month, ending in September. We will announce the times and venues on the CASIS website and also on the Newsline. We're going to try very, very hard to get the lectures and the videos that we're making of this series posted on the CASIS website. Our plan is to have all this information up on the CASIS website before the next set of lectures come along. And so that's certainly what we're shooting for. So with that in mind, our next lecture is on Thursday, May 30th, back in this auditorium right here, the Armadillo Room. Finally, I also want to mention that there is a Signal and Image Sciences workshop that will be occurring a week from tomorrow. It's called the CASIS Workshop, and there's a lot of different kinds of signals and systems that we'll be doing there. Lots of presentations on machine learning, graph theory, applications of signal processing, seismic signal processing, non-destructive evaluation. We have an excellent keynote speaker from the Lehigh University who will be talking about the Internet of Things and how to detect cyber attacks on the Internet of Things. That'll be at 1 o'clock. We also have a featured speaker who will be Greg Spriggs from Lawrence Livermore here, and he'll be talking about how to, his analysis of historical video data of atmospheric testing and to reevaluate performance. So that ought to be a very, very interesting presentation. The CASIS workshop is again sponsored by engineering through the Center for Advanced Signal and Image Sciences and also the IEEE, both the Signal Processing and the Communication Society. So hope to see you all out there. If there aren't any questions on the administrative materials for this, I'll turn over to Jonathan. We'll start the lectures.
Okay. Do we want to dim the lights or anything? Or that's fine, everyone can see that? So we're starting with this. This is what quantum is. It's amazing. It's got a lot of cool stuff going on. So this is very much an introduction. Thank you for taking the time to come out and listen. Hopefully it won't be a waste of your time. So I'm just going to stick to what was sort of in the description of this initial lecture. So I'm going to give a really rough idea of what the basic ideas of quantum computing are, what a qubit is, and things like that. Give you some notion of, in terms of quantum computation, why it's useful. So it's basically what kinds of problems can be accelerated in principle on a quantum computer. Tell you a little bit about the context. So there's a lot of funding opportunities coming out. There's a lot of interest from the national government and also foreign governments in this space. So to tell you a little bit about that, and then I'll finish my part with a brief summary of some of the activities that are going on now at the lab. And then I'll turn it over to Steve, who will give a little more in-depth introduction to the state-of-the-art in quantum sensing. All right, so what is quantum computing? Basically, it's a notional generalization of classical computing. That's one way of thinking of it. So in classical computers, the fundamental object we usually think of are bits. And you can set bits to have some value. You can apply transformations to those bits. We call those logic operations. So you might do something like not and or and build things up, and eventually you have a CPU and an iPhone and so on. So, right? So the quantum analog of we start again with a bit. Here we're going to have a quantum bit or a qubit, and this is where things start deviating from that that description. The basic idea of a quantum bit is a two-level quantum system. And the way that differs from the classical notion of a bit is that quantum states, we usually talk about the state of a quantum system in terms of a vector that has some values. These are complex values. So your one quantum bit can have an arbitrary value, set of values, alpha and beta, and the only thing that really constrains them is that the sum of them has to be equal to 1. Now, the connection with a bit here is that now these states, this is the equation for a sphere, surface of a sphere, right? So these states live on the surface of a sphere, and classically, you could imagine your classical bit being 0 or 1, one of these states, and those are the only ones that are allowed. The quantum analog of that fundamental unit of computation is this, all possible points on this surface of the sphere are allowed, and those are the objects that you're going to manipulate to perform computation. Now, if you want to get sort of philosophical or excited about what this means, you can think of, all right, classically, 0 could be, say, true or false, and 1 could be the opposite, and you can express logic in terms of chains of those states. In a quantum system, using this unit of this fundamental unit, which can be some arbitrary superposition of those, you can imagine the state of your system could be true and false, true minus false. You know, it's a bit odd in the sense that anything on this equator here would be some combination of 0 and 1 with a relative phase. So what good is that? Well, I'll get to that in a minute. But what happens when you, the sort of real magic happens when you add another one of these. So if you have 2 quantum bits, oh, sorry, I jumped ahead of myself. Just like in a classical system, if you're going to do a logic operation on this, we can think of quantum logic operations. So quantum computations would be built up from units of basic logic operations on the space. And effectively, you can think of them as rotations on this sphere. So they're transformations that take you in some controlled way from one part of this space that we're now defining to another part. You can think of it as your Turing ticker tape, but now it's living on this hyperdimensional sphere. And so, like I was started to say, the magic comes when you add a second one. So here I'm representing 2 quantum bits, and the point here is that when I've done that, the size of the space that I need to describe that is now a vector with 4 complex values. And that trend essentially continues as you add more quantum bits. The size of the space that you're describing with the state of the quantum system is growing exponentially, 2 to the nth power. And so now you can kind of, if you weren't already familiar with all this, now you can kind of get some notion of where the power of this is coming from. You've got some n objects that you can do computation on, but the effective space they're operating on is growing exponentially. Just like in the single quantum bit case, the algorithms or operations work in a similar way. You have transformations on that 2 qubit space. An example might be, just like you might make a truth table classically, you can have a transformation table like this for your starting state. 0, 0 goes to 0, 0. And here the only funny thing is that 0, 1 goes to 1, 1, and that would be called a controlled knot. And what it turns out that you can prove, at least mathematically, if you have this particular gate, this controlled knot, and a certain set of rotations on individual qubits, then you can do what's called universal computation, quantum computation, in analogy with universal classical computation. So you know how if you're familiar with the Turing tape, the ticker tape, if you can do a certain set of basic operations, then you can do universal calculation. In the quantum case, if you have this certain basic set of unitary transformations of the quantum states, effectively you're guaranteed to be able to reach any other point in the space, which effectively amounts to being able to do an arbitrary computation in that space. All right, so now that we're done, we all understand quantum computers. What goes wrong with these systems, and why don't we have them now, and so on? Well, the fundamental issue is sort of twofold. One is, I just said, effectively, I described something which is analog. It can, my individual unit of my quantum bit, I said it could be any value, right? Well, we all know that digital electronics is nice for a reason, you know, and that's because you can correct errors. Digitization is the sort of the miracle that actually allows us to do computation at scale. So that might give you some pause right away thinking about quantum. I just told you I've got this magic system. It can do anything. I just have to transform it. I can transform it in arbitrary ways. Well, it's pretty much just like an analog computer at that point. Now, on top of that, the fundamental problem with analog computers is noise. And it's no different in the quantum case. So I just talked about building this quantum bit. Presumably, it's this nice magical object that's purely quantum mechanical. And I'm able to go in and manipulate it so I can do these operations on it. Well, the fact that I'm able to go in and manipulate it means that it's coupled to the outside world in some way, which ultimately means it's not an isolated system. It's coupled to the environment. And so it's what's called an open quantum system, meaning that there's no way to perfectly isolate that quantum state. It's never going to exactly act exactly like these two levels. And the way that materializes in practice, if you build a system like this and you prepare it in a state, say at this point, and you come back a little later, you'll find that it's dephased. It basically got kicked around by interacting with the environment in some uncontrolled way, and it's not in the state I left it in. And the net effect of that over time is that instead of having this wonderful arbitrary state on the surface of a sphere, I just get a random number. Here I'm representing that by a point in the middle. This would be basically a coin toss. I measure the system, and I'm going to get 0 or 1 50% of the time. I have no way of extracting any additional information from it. So what this means is that in a quantum computation without error correction, there's effectively a clock running the whole time. You initialize the system in some predefined state, say the 0 state. I'm able to clear my buffer, and now I start doing things, and if I don't do them fast enough, the system is basically turning into a random string. And that's one way of understanding sort of the fundamental challenge, I would say right now, the current state of the art in quantum computation, is overcoming this formal limitation of the physical systems by being able to correct errors as they occur. And I'm not going to get into it in this lecture, but there is, again, a formal mathematical proof that suggests that you should be able to correct errors with arbitrary accuracy, and so that you should be able to do universal computation without introducing exponential overhead, and so you'll still get all these speed-ups that quantum processing is supposed to give you. So what are these speed-ups? Well, one of the most famous things is Shor's algorithm. Who's heard of Shor's algorithm? 50%. So you know about like RSA, and we have this token that I won't show you, and you use that to log into computers and so on. So one of the foundations of much of modern cryptography or cryptographic protocols is based on factoring large numbers. And the reason why that's a good thing is it's pretty easy to represent a bit string that's long, 1,000 bits. And if you can ask the question, well, what are the prime factors of that? It turns out it's very hard. Classically, the cost of evaluating that brute force would be to evaluate every possible number between 0 and that, and see if it's a factor, see if it's a prime. That's sort of the naive picture. And so there's going to be 2 to the n options there for an n bit string. So that's a good cryptographic protocol. It's something where I can have a secret. It's hard for you to brute force figure out what that is. Now, Shor's algorithm was one of the first sort of real major achievements in formal quantum information science, I would say, and it basically shows that you should be able to factor a large prime in some time that's polynomial, roughly linear in the size of the number of bits, compared to here exponential for what you could expect classically. And the basis, I'm not going to get into the details of how it works, but the basic principle is actually pretty easy to understand if you're familiar with the Fourier transform. We've got the fast Fourier transform. That's pretty nice. It's already fast, right? And in terms of classical algorithms, it's a pretty fast algorithm. The issue is if I'm trying to do a Fourier transform on an exponentially large space, which is, say, all possible digits of an n-digit string, then even with linear scaling, the fast Fourier transform has an exponential cost. The magic of the quantum case, the quantum analog of a Fourier transform, allows you to do that in a number that's proportional to the number of quantum bits rather than the size of the space that you're operating on. And so it's an exponential speedup. That, with some other really cool, clever things, lets you do factoring of large numbers in polynomial time with a quantum computer that doesn't have any of these problems. So you assume this stuff doesn't exist, and then you're set. Okay, so that's a main driver, I would say, for interest in quantum computing. Something that's a little more relevant for us at the lab, or at least that's interesting and relevant for me, is another hard problem that we have a lot of difficulty treating exactly with classical computers, is understanding the dynamics of quantum systems. And in some sense, that's the basis of all the scientific computing that we do in support of the NNSA mission. We've got physical systems, their dynamics, their properties are fundamentally determined by quantum dynamics of some form. We've got some pretty good approximations for treating those, but they're not necessarily all that good. They certainly aren't controlled. And so one of the original notions, the birth of quantum computing in some sense came from Richard Feynman being annoyed by this fact that it seems really hard to simulate quantum systems. The size of the space goes like 2 to the n, where n is the number of particles or something. And why should a computer have to take so much longer to do this? That means it costs an exponentially large amount of operations to simulate exactly quantum dynamics. So why should a computer have to have so much trouble? And that's he's basically said, well, let's come up with a new kind of computer that uses quantum mechanics. Now, that's a little bit revisionist. I mean, there were other people thinking about quantum computers too, but it was one of the original motivations to say, nature can do this, why can't we? And it turns out that you can prove also, in that case, that you can simulate the dynamics of quantum systems efficiently with a formal quantum computer. And the speed-up is similar to the case with the Fourier transform. You've got something which would be exponentially hard classically. It ends up being polynomial or ideally maybe even linear on a quantum computer. A neat thing for general applications is that the basic thing that's going on in the background here is a manipulation of a large linear system. That's led to a whole another class of algorithms that allow you to have exponential speedup in evaluation of general linear systems. So then you get into saying, well, wow, maybe a quantum computer could actually allow us to accelerate everything that we do that involves some kind of linear transformation. And then it seems really potentially impactful. Okay, so where are we at now, and where are we going, and so on? Why is this exciting now? The main thing, I think, is the reason why there's interest now is people are starting to build these things. And companies are getting interested in this, and you can log in now online and program a quantum computer and run a small quantum program. And so the interesting thing there is that there's something that at least various people would like to imagine is happening, which is that the number of quantum bits that people are actually building in the lab is growing every year, and it looks almost like a Moore's law kind of thing. So right now we've only got, say, tens of quantum bits, so the total size of these systems isn't that big, but it looks like you're getting more all the time. And if you ask when would you have enough resources in one of these systems to do something interesting, and roughly speaking, it happens fairly soon. It happens maybe in the next certainly the next 10 years. And this is geared towards our NNSA mission. These are potential things that could be impacted. I'm not trying to imply here that, oh, suddenly you're replacing classical computing with quantum computing and you're solving all this with this. This is more like, this is a time frame where you could do a demonstration that would show that this technology has potential significant impact, which means that right now you can't do a demonstration that shows that. So another sort of fly in the ointment here is that I'm using the number of qubits as a proxy for the power of this quantum system. That's actually not accurate. I showed you before that they have noise and so on. So far, no one has shown that you can actually, in the lab, systematically correct these errors. And so the actual useful number of quantum bits, or the size of the space that you can actually manipulate, isn't growing nearly as quickly. That's what this line is supposed to show, and it's not even clear that it's growing that at an exponential rate. So these are your really optimistic and your not so optimistic pictures of where this is headed. Regardless, there's a lot of money being spent. I'm sorry, it's being recorded. There's a lot of interest in this area, not in the least from Department of Energy, from the federal government. So this is just a selection of sort of these basic research needs in X that have come out of the Office of Science. We've participated in many of these. You can go on the DOE website and see them, and also in your particular area at the lab, there's almost certainly one that's targeted for you. So there's from OSCAR, from BES, from Fusion Energy Sciences, Nuclear Physics, and so on. And there's pretty large calls that have come out starting about 2 years ago from Office of Science in this space. I think the running total so far is a couple $100 million that's been invested over the last couple of years. So it's grown very quickly in Office of Science. The other thing that's happened recently this year is that Congress passed this law. Was it a law? Oh, sorry. For the National Quantum Initiative, and the target, main outcome of this is that they're going to set up 4 to 5 centers nationally. Each of them will be funded around $25 million a year for the next 5 years. So that gives you some idea of the scale of interest. So what's going on here? We're actually doing quite a bit, and we're most of it, I would say, well, so here, one of the main things that I'm excited about, and you'll learn more about as the lectures go along, is we've set up a test bed. So we built a quantum computer. Just like in the early days of classical computing, if you wanted to really understand these systems, the best way to do it is to try to do it yourself. And we've done that, and we've actually done some pretty innovative things. So this is largely geared towards trying to understand that time scale. When can we realistically expect these impacts on our sort of NNSA mission space type problems? So we're looking at relative toy problems right now that are mapping to them, so like small nuclear system dynamics, some physics-inspired problems, I would say, in quantum simulation. Another significant area that's been going on longer at the lab, we have a big infrastructure and big investment in computational materials design, computational materials optimization. A lot of that involves things like density functional theory, quantum Monte Carlo methods, being applied to trying to understand specific issues at the atomistic level in a particular material that would impact the performance of some system. That's especially relevant for these quantum systems. There's, in fact, there's maybe this is a little bit of a digression, but that 0 and 1 state I told you about, the energy associated with going from 0 to 1 in a typical quantum computer is on the order of microelectron volts. If you think of that in terms of a temperature, it's around 100 millikelvin. If you think of that relative to like the energy of a fly beating its wings, it's about 6, 7 orders of magnitude lower in energy. And it turns out it's in a regime where we basically don't even have the tools to measure, other than by building a quantum system to measure it. We certainly don't have the first principles knowledge for doing the simulation accurately. We can't predict energy differences at that energy scale. So it's sort of a frontier in material science and computational material science in particular. So we're working in that space. And then the other area, which Steve will get into in much more detail, is sensing. And we've got a number of projects in that space. The basic name of the game there is, well, I told you these things are very sensitive to the environment. That means they're good sensors, right? So you can use the fact that it's not necessarily doing what you wanted as a computer as a way to have very, very precise information about the environment. So this is our quantum test bed. I'll tell you a little bit more about it later. It's real. It looks funny. This is a refrigerator. A lot of pictures you see online, by the way, if you do a search, Google image, quantum computer, you'll see this thing that looks like a golden chandelier. It's actually a refrigerator. You're not seeing the computer. You're seeing a refrigerator with a bunch of wires going into it, and more about that later. But this is our refrigerator with not so many wires. It's a very good thing. And I'll just wrap up. This is sort of our posture, I would say, at the lab. We're working in the materials. We're working in the device physics. We're working in the simulation, trying to understand near-term applications of these systems, and also in quantum sensing. And we've got we're basically open to collaboration and very interested in making those kind of connections. So that's the end of my part, and I'm going to turn it over to Steve.
Let's see if I can drive this thing. So you say I can go forward, huh? I can. So quantum sensing. So pleasure to be here, just like Jonathan was. And the message that you had at the end of your talk is a good one, is you may see other applications in this that excite your imagination, and I would love to collaborate with any and all. So quantum sensing, let's have a go at it. And again, like you described in greater detail later, we'll have lectures that dig into a lot of the specifics here. So in a somewhat self-indulgent way, with the pictures here that all are sort of taken from my life in quantum computing, let me introduce the subject. So first of all, why are quantum sensors good? And I have to prove the point to you. They offer very, very high precision. They are, despite the give and take of how the world around them perturbs them, they at least allow, in principle, high control and isolation. Because they're based on really directly addressable fundamental physics, they're intrinsically self-calibrating, whereas devices otherwise are hard. And we'll give examples of this. And they, and then in a sort of more technical level, they don't have baseline drift, like let's say the scale in your home, in your bathroom that you get onto. When you get off of it, you notice it isn't reading 0 anymore. Quantum computers, quantum sensors and quantum computers are very good at not getting that wrong. So we're very good at fast applications, and you'll see some of those. This work is very synergistic with quantum computing. In particular, and Jonathan was mentioning some of the basic gates. Turns out that there are direct analogs in our essentially qubit manipulations that we're using to sense things and so on in the environment. So Hadamards, Paulis, CNOTs, and so forth have their direct analogs in the sensing protocols that we do. Applications, you've heard about all of these quite a bit before: atomic clocks, field and force sensors, which of course is the center of what I'll probably focus on here. Inertial navigation, spooky, don't have to do anything. Metrology, fundamental science. Examples that we're particularly coupled to here are, for example, axion, dark matter detection, and eventually gravitational waves and so forth. Turning a little bit more personally to things that I've been involved in, so the talk is going to shade over to, it's all about me, is atomic fountain and Sagnac interferometers to do what? To do a kind of gravity tomography. So no hands, I can see inside of a box to tell you what the mass distribution is there. So that had, clear applications that we'll talk about. For example, is there a threat passing through a portal, the George Washington Bridge Toll Plaza? And then the other one, which again, sort of sings along after a classic sensor modality, it's out there in every airplane you fly in, is a Sagnac gyroscope to do dead reckoning navigation and all of its typical applications. So what you see in the pictures here is the setup up at the corner of about from 7-8 years ago. This work, by the way, was in collaboration with AOSense, a Stanford spin-off company on the peninsula. We borrowed a sensor that they made under DARPA auspices to demonstrate gravity tomography in the near field. We really did. This sort of poster child here showing the basic Rabi oscillations of the atoms that we'll talk about in detail that are the basic gravity sensor, and then a picture at the bottom of the version of the thermal beam sensor that we're using for gyroscope. So this is something you might like to read later. There are lots of physics modalities that are useful for sensing, and they come in different quantum flavors. So I'll talk about some of the modalities in a second, but let's talk about the different degrees. And I hate this, the whole world is quantum mechanical, so what is this quantum thing? It's all of us. But different degrees of quantumness, I'll violate my own rule there. So the lowest type, which is called type 1 on this chart, are things that simply exploit just the gap in a typical quantum mechanical system. For example, the basic qubit two-state system. But they're not exploiting any other phase coherence or anything else, just that. Type 2 is exploiting phase coherence, which gives us a lot of extra control over what's going on. And then finally, the one that was really cool is ones that exploit true quantum correlation, for example, Bell state correlations and things like that. And we'll see that that really enhances our ability to detect stuff. And so, among the different things here, not to dwell on it too much is, for example, neutral atoms. That's pretty much the theme song of my involvement with this, which are looking at hyperfine transitions, basically, in a very carefully selected alkali atom. Those, at least on this chart, are labeled type 2 and type 3, exploiting phase coherence, and then nowadays, exploiting actual entanglement and so on. Trapped ions, so singly ionized species. We're also involved in ion trap quantum computing. It has direct analogs here for sensing that are pretty much in a similar mode. Again, with microwave interrogation, optical interrogation, so forth. There are Rydberg atoms. Many of you have heard about NV centers in solids, which are beautiful local magnetic field measurements. Squids obviously have an ancient history, and the list goes on. So, there's a lot of different modalities here of different qualities to do quantum sensing. And sort of examples, there's a kind of a duality here of the two most famous things. In an atomic clock, and we'll discuss the details of how the sensing for that works, the idea is to have something that's in a very well characterized oscillating system that I can probe or use it even to train a local oscillator, but not have it be so perturbed by the environment. So for example, in atomic physics speak, a typical case that we would have is, the classic atomic clocks going back to the 1950s involved a hyperfine transition, which is substantially immune to external fields that are on m=0 states. So for example, the transition shown here from, F3 to 4 on the magnetic quantum number 0 line. On the other hand, the field and force sensors are sort of the opposite. It's basically a clock that we've allowed to be messy. So it's timing what's going on in our environment, but we're wanting it to be perturbed by the environment. And you'll see the give and take between those things. I have, by the way, sprinkled a set of references throughout this that I think are pretty good. This Reviews of Modern Physics article is a particular favorite, so go for that. And to do that. Let's talk now about, this is sort of the core of what I have to tell you. What's the basic protocol of quantum sensing? So we're talking about detection. We're talking about typically an interferometer setup of some kind, exploiting phase coherence. And then finally, what do we do about noise in these kind of systems? Do we live with it? Do we pretend it's not there? You know, things like this. So the basic protocol is shown on the left. The first thing that we do is we initialize our system. So we set the thing up, for example, in the ground state of a two-state qubit system. We set it in the zero ket state or something like this. And that could be, going back to the sort of block sphere picture that Jonathan showed, this could be, imagine a magnetic field measurement. And so then the typical measurements I'm able to do is to see, you know, Stern-Gerlach apparatus or something like this, that the magnetic field is on the up and down z-axis. But I want to know what's going on elsewhere in the system if the magnetic field is waving elsewhere. So what I typically do is I initialize the system, and then I tilt it over by what's called a pi/2 transformation to the sort of equatorial axis that you saw in his picture, and then let the external fields play on it, tilt it back up again to measure the magnetic field. It's of course going to be off a little bit from the North Pole, and see what I get. So said in sort of mathematical speak here, let's say it again. What we start out with here is we initialize in the we initialize in the zero state. And then we tilt the system over to something that we're interested in, which is the beginning of a mixture of, let's say, the lower and upper state of our system, which is the system that's going to start to oscillate. We turn on, in this case, let's say it's a clock, we turn on time. So what's happening to the next step here is that, let's say we indicate that the energy difference in the system, h bar is 1 in this case, you know, the upper state is oscillating with a frequency omega 0 relative to the lower state, so that what happens is this wave function, there we go again, is basically oscillating, and then I go and read out this state. So how much is in my lower state, how much is in my upper state, with just the probability, you know, through some sort of readout system that's telling me I'm in the upper state. And what this is doing is, in this simplest quantum protocol, which is called Ramsey interferometry, is I'm basically able to get, by looking at the fringes that take place, this simple formula for the probability of detection here, over there, I'm able to get a very good measurement of omega 0, AKA I've made a simple clock out of the system. And then I might use that in some fancy, weird electronic way to train a macroscopic oscillator or do something else. So this is sort of the clock modality. In general, I want to turn a little bit to the noise story here. I'm interested in measuring stuff that has an extra term in my Hamiltonian. It could have been the magnetic field measurement I alluded to. So I have a magnetic moment, let's say called mu in this equation here, and it's talking to my field F or something like that. And I want to see if I can measure very small values of F. And, you know, what we've written down here is a very simple formula that says, you know, what's the lowest phase measurement that I can get in that block sphere tilt and measurement that's going to tell me the lowest magnetic field I can measure. And basically, it's related to two different things. One is the quantum mechanical jitter or error in this phase measurement phi, and then it's divided by the measurement time, capital T. And that, of course, is going to be limited, again, turning back to your talk, to how long this thing stays coherent and is reporting the correct kind of information. It doesn't stay coherent forever. So a slightly more correct form is shown over here. There's a time called T2, which is basically telling me the phase decoherence time of the system, the extent to which if I tilt it over to the equatorial axis that I'm jittering around and that I'm off in the system, how wrong that is, and I get a minimum value of the detected signal. It could be anything that I'm interested in. Eventually the gravitational field that I'll show you soon is related to this decoherence time, the measurement time, and then I have to answer to you as to what kind of error we're getting in the phase, delta phi, and that comes in several different flavors in this business. What we're talking about here is the crudest version of this, which goes by the techno-speak name of quantum projection noise error. It's sort of atom by atom detection. It's the crudest way we do this. The sensors and stuff that I'm actually going to be telling you about are all in that mode at the moment. So then delta phi in dimensionless units goes like the reciprocal square root of the number of atoms or measurement steps that are statistically independent of each other that I did. In the future, which is happening right now, squeeze state detection, which is equivalent to using Bell states, and then things beyond that improve this quite a bit. And I have some more references here for those who are interested. So turning to a particular point example that shows how we do this, let's talk about neutral cold atoms, to use them both for gravitational sensing as well as gyroscopic sensing. So all of this spins off of the ability to clean out, which you would typically have in an atom in an environment, all kinds of excited state population. Obviously, that's very bad for those simple formulas I showed. I want to know that when I initialized this system, it was actually in the ground state to extraordinary accuracy. So what I need to do is remove all the other states. So first of all, the translational degrees of freedom. I have to cool the system down so it's moving around very, very sluggishly and under my personal control. And then, by the way, as a subsidiary thing, I need to remove, using tricks with microwaves, lasers, and my wrist and so forth, all kinds of internal atomic states have to be removed as well to get the system into the ground state. So the go-to method for this is, at least for atom vapors and so forth, is laser cooling. The 10-second introduction to that is the way you do that is you have 6 beams coming in each of your axes, and you tune them to the red side of a spectral line that you like, so that if this not cooled yet atom is moving toward your laser, the Doppler shift gives you a little extra oomph and makes it resonant with the beam. So they oppose each other, and you therefore, from momentum conservation, tend to slow the beam down. If the atom is running away from the red-shifted light, it's even less resonant, and so it talks to the laser beam on the other side. It doesn't get accelerated or anything bad. And that's the basic idea. This was first demonstrated by Steve Chu, Claude Cohen-Tanuji, Bill Phillips, other people in the 1980s, Nobel Prize 1997, I think. And that was the thing that just set this field ablaze, basically. I want to comment a little bit on past physics history that some of us may be old enough to remember, because I was talking a little bit about showing you soon an interferometer that does gravity measurements to high precision based on a cooled atom, or in the moment case that I'll describe, cooled neutron version of a Mach-Zehnder interferometer. So if you tuned in the Wayback Machine to 1975, a beautiful, beautiful paper in PRL written by Al Overhauser and other people, showing that you could do exactly what I'm saying with relatively cool, actually neutrons done at argon that were used for solid-state physics measurements. And they set up a kind of Mach-Zehnder interferometer with crystal beam splitters, I mean, literally with my hands, some macroscopic thing like this, where the neutrons come along, they're split into 2 loops, one that flew a little higher in the gravitational field than the other, recombined, and then you read out. And if you look at that paper, you'll see it's pretty convincing that they see the gravitational field of the Earth. What I'm going to be claiming to you very shortly here is for the applications we have with a full quantum sensing protocol, we go, I want to say, probably 10, 11 orders of magnitude beyond that for sure. So this has come a long way. Really repeating what I told you about the measurement protocol a few minutes ago, I want to retell you the story, but now in sort of more atomic physics language. The basic Mach-Zehnder measurement protocol in the atomic fountain is I've cooled my atoms down. Everybody's in the initialized state that I showed you with the Ramsey interferometry, but I'm now going to do something with it. I launch the atoms up into a fountain going up with moving optical molasses. I detune my lasers differently to do that. And then in the simplest version of this, I basically have 3 additional laser pulses in the system. That thing I called the pi/2 pulse, which tilts me over in the Bloch sphere. Here I'm using it to make a kind of entanglement between an internal hyperfine state, which are labeled here 3 and 4 for the particular case, I think in this case of cesium, and then coupled to the momentum of the system. So what I've basically done is I put a nice ticking atomic clock on an atom that's flying up and then is being dragged down by the gravitational field of the world around it, and the clock is telling me what time it was when I was at a given position in the system. So there's a kind of a cartoon here of this shown as a Rabi oscillation. I need to read out, of course, what the atom is doing by recombining it at the end, so I need a subsequent pulse to do that. The added technology that makes this doable, which allows me to take what's effectively a stroboscopic movie of a falling atom or a rising and falling atom, is, let's say, stabilizing a laser, you know, an optical or spin-off of telecom industry laser that's, let's say, 10 to the 15 hertz at some form to maybe 10 or even below that kilohertz in stability, which allows me to take this very, very precise movie of the falling particle. And so, for example, you know, really the underlying physics of this in a semi-classical way is very simple. My sensor is, I want to see, beside the Earth, you know, making the fountain go up and down, I want to see if I put a bowling ball over here, what it's really doing is tipping the atom slightly to the side. I want to see the phase shift that's due to that, how much tipping took place. You know, let's say in the course of flying up and down about this distance and falling back again. It's, as I say here, it's about, I don't know, it's about half an angstrom, which should strain your credulity. But in fact, with the laser stabilized this way, it's easy to see that. So just a little bit more for just a second about the atomic physics. This is a pretty typical setup. Very, very clever trick that goes back to Chu and Mark Hasovich's thesis at Stanford in the early 90s. This is a case of having your cake and eating it too in physics. The clock-like transition, which is down here, that is largely immune to external perturbations is in this multi-gigahertz hyperfine transition. However, we want big momenta attached to this thing so that the atom wave packet spreads out so it sees a big gradient in the local field. So I do that with nonlinear Raman scattering, which is shown by these two beams here, and these are not to scale. I mean, this is basically this sort of 10 to the 15 hertz kind of number, and this is 10 to the 10, so that there's a very, very clever interplay of a pretty powerful laser that's operating, you know, in the near visible, in this case, with something that's living in the microwave. And anyway, I again feel the desire to retell you again what I did in different language. You know, you're going to go home tonight and your kid has a physics homework problem and they want to measure the local gravitational field, and please don't say a pendulum, because a pendulum has this non-quantum sensor thing associated with it, which has got a string or a wire attached to something. And to understand a pendulum at very, very high accuracy, you've got to get into the physics of string or of metal, which you can do, and by the way, that's been done magnificently. I don't want to undermine that. But what's done here is something actually simpler. It's you drop a rock, or an atom in this case, in vacuum, let's say, or in air, and you simply take this stroboscopic picture shown in the left-hand side. I take a picture, my clock is ticking, I take another one, and then another one. I add those two distances, subtract twice the one in the middle, and that's my acceleration. And in fact, in disguise, that's exactly what I'm doing, shown on the right with the phases of these atoms as they're ticking along. I want to spend a moment, because it does connect to where this is going, to connecting this sort of discussion for gravity to metrology and fundamental science. It turns out, despite my snarky remarks about pendula and so forth, that very clever mechanical gravity measurements have been done for centuries, going back to pretty much right after Newton, you know, Bouguer, Cavendish, and so forth. And in really interesting things, particularly in geology, were done, you know, with sensors like that. You know, an example shown on the top of the picture here is a kind of boiled down version from the University of Washington, from Edelberger's group, of something which is essentially the grandchild of the Yotvosh torsion pendulum that was used to demonstrate the principle of equivalence in general relativity, and is now one of the go-to methods to really probe fundamental gravitational physics in the laboratory. We're really describing a rival to a mechanical sensor like that, where we're trying to use atomic physics to measure these things to high precision. And again, it repeats the point, particularly with our applications. Sensors like these certainly have their incredible place. However, if it comes to something in the field on a moving platform where there's no week-long setup time, which is what the analogs of these things are typically doing in geology, we feel we have the edge of the system. The other thing, which touches back both on fundamental physics and on the applications, is right now, being the last 5, 6, 7 years, there's a disagreement brewing between, let's say, the Adelberger group as a point example, and the 2 or 3 rival groups doing atom interferometry, we with the Stanford folks being one of them, now Tim Cavacci at Northwestern, and then the Tino group in France and Italy. The atom people are getting an answer for the value of capital G, which we claim is good to part in 10 to the 4 or 10 to the 5. The torsion balance people are getting their answer, which is getting more precise, I guess, using that word carefully, but they're becoming to disagree with each other at the 4th or even cruder level by more and more. And what this is probably showing, and people are interested in figuring this out, is probably it's not a matter of, we don't understand the fundamentals of gravity at this kind of level. These are basically Newtonian measurements. But we're not understanding, and this is important for applications in the eventual quantum sensing modality, we're not understanding the specific error budget of these things, including quantum corrections, well enough. And so it's probably going to impact our applications quite a bit, answering a question like that. And then the rest of what I've shown here is really, there were attempts going back to the 1980s to use, you name the geological instrument, to look, for example, underground structures and tunnels and applications, and they tended not to do very well, again, because of this difficulty in setup time that we claim that we have solved. To continue the brag for just a minute, and this is real data actually, this is a log-log plot of the 2 basic figures of merit in, let's say, gravitational sensing that you care about. So one of them that I alluded to a moment ago with your getting weighed in the morning is the bias drift, the tendency of the sensor to not report back 0 after you've tried to reset the system. The other is called scale instability, and that's the following point, which is on the other axis in some sense of measuring. You are wanting a order of magnitude by order of magnitude linear report of the microscopic atomic physics of the sensor translating back into some kind of macroscopic read in the system, and then that has a wiggle about it, and so that wiggle is scale instability, and that's shown here in various orders of magnitude. And so this is an example of, again, real numbers of how atom interferometry compares to the best sensor, the best mechanical IMUs, such as devices that are in your phone, or actually specially prepared sensors like these floating microresonators. From those kind of considerations, and again, it sort of touches back on what I said before, if we're doing what's called gravity gradient measurements, the quantum sensing error that is typical of the system goes like this equation here, where basically the time of the duty cycle of the Mach center interferometer goes with the laser effective momentum and the separation between them, and then that ubiquitous square root of n factor, which is typical of quantum projection noise. And again, that's going to improve by orders of magnitude as time goes on. So what does some data look like for a sensor like this? This is just before I began to work with AOSense. This is the instrument we used for the feasibility study showing gravity tomography, not run in a gradiometer mode, but just run as a gravimeter, which means measuring the local value of little g. The simplest, that you think of is the 9.8 meters per second squared, but then beyond that. So this is the variation of that number. Forgive the sudden switch to CGS units, so it's in microgal. As a function of about a 10-day period in the lab. And of course, everyone here, I should hear some oohs and ahs when you see this. This is showing the earth tides in the laboratory as a function of time, and you see the 6-hour variation as the sun and the moon begin to move over this 2-week period. Those numbers change, and you're seeing what is really going on here. This thing is so sensitive that you're really, when you're measuring the earth tide, what you're really doing is the earth under your feet, just like the ocean, is stressing by maybe a foot up and down, every 6 hours or so. And you're moving closer or further from the center of the earth by about that foot. And what you're seeing reported here is the variation of your GM over R squared, because R is changing a little bit, okay? And if you just quickly compute in your head, basically the derivative of that expression, you see that this is about the right order of magnitude, if you believe me, that it's moving up and down by about a foot. There's another important lesson here for quantum sensing, which is, as cool as this is, and it fits the earth tides to geological satisfaction, I am told. I'm not a geologist. But there's something wrong here. And you notice all that black jitter that's there and so forth? That is vibrational noise that occurs on the shake table or non-shake table on the big nailed-down table where this thing was being done, and that is death to our sensing mission, because that is of an order of magnitude that is probably 50 times too large to do the yet-to-be-described gravity sensing of a passing vehicle going through the George Washington Bridge toll plaza. And so what you need to do to fix this, at least as far as we know right now, I mean, in some sense, Einstein, literally and metaphorically put his finger on the scale, all accelerations being equal. You can't, unless you know something, get rid of that black vibration. But what you can do is the following, which again is sort of, in a sense, a sort of general relativity thing, is you can do gravity gradiometry, which is have two sensors like this, have them driven by a common laser system so that if they vibrate, they go up and down together, and you look at the difference between these two. You look at the derivative of the local acceleration, and of course, that works great, or I wouldn't be standing here bragging about this, but there's a penalty, which is when you do that, the range of the sensor carries an extra factor of 1/r. So keeping that in mind. Why did we work on this here at Livermore? Well, okay, so this is an unclassified picture of about 2,000 examples of things that we might like to detect, radioactive stuff that might be in a vehicle. It could be a real nuclear threat, it could be material, and it's plotted as a function of the exterior radiative flux, wherever it came from, in gammas and neutrons. And it's, by the way, a log-log plot also. And the point is that stuff in the upper right-hand side here is pretty hot, and the standard radiation sensors can detect it, we hope. However, the things shown in color over here, it's a challenge because, they're made out of something that's not that radioactive in the first place, like uranium, or they're shielded, or whatever the reason is. Those are challenging. So the challenge that DHS put out there that I think we satisfied is, can you passively, X-rays would do the job, but they're not allowed here clearly, can you passively determine that such a thing is present in real time? And I think we demonstrated that we can do that with a sensor that is all the moving parts exist. It's probably a factor of 10 more sensitive than the feasibility study that we did. This slide is way too busy, so I'm going to skip it. It has a lot of numbers that can remind me if someone asks me a question of the size of these effects. But it's much more fun to talk about our feasibility study. So this is a picture of the same sensor that AOSense had, or at least inside of its magnetic shield with sort of length scales. And the idea was to see if we could see inside of that yellow box, no hands, double-blind experiment. We put roofing foam inside of the box, took a scissors, cut out shapes. Roofing foam is very strong, weighs nothing. So you put, let's say, a tungsten cylinder here, put a sphere here. They look from a gravitational viewpoint like they're floating in free space. And so we wanted to see, could you tell this mass distribution from that one? And we think we could. And so the box, the sensor was, this was for the Navy application, so it's pinned down. So we moved the box up and down on this translation stage, and there are 2 point examples of the positions of the cylinders inside of the box, primarily differing. The total mass, by the way, is the same by simply turning them sideways. So the center of mass has moved away from the sensor axis by, about this many centimeters, something like that. And so then, could we, from the gravitational signal alone, see the difference? And we could. An example of some of the data is on the right-hand side, or a little bit higher quality story is over here, showing 2 of the cylinders, in this case even more indistinguishable from each other, touching each other on the wall next to the sensor axis or separated. And we could readily tell them apart, which was kind of cool. In fact, what began to convince sponsors is when we did this, I wasn't even there anymore. You get a text file with a bunch of phase numbers on them, and we were able, using hypothesis testing, to tell one from another. Yeah, the time has come. So this is your favorite slide, Dave, right here, right? So in a sense, the talk could end here, right? So this is a beautiful piece of work that Dave Chambers did, we were working together on this, actually demonstrating that if you had a portal-like setup, that you could basically disentangle the mass distribution of a passing vehicle. And so I think actually later, probably, Dave will give one of the lectures and talk about the signal analysis that went into this story, but it worked quite well. The mass cloud of an object car, the Toyota Yaris is shown there, and so forth. but I've been asked to accelerate, so I will do that. Let me at least spend a moment on the gyroscopic sensor, and then we'll go on. So just as the atomic fountain as the gravity sensor was a version of a classical optical setup, Mach-Zehnder interferometry, our other favorite is a Sagnac gyroscope. So, basic special relativity point is, if I'm going around in a circle and I'm in a rotating frame, there's a difference between rotating this way and rotating that way, because I'm with the direction of rotation or not. If my particles are going around this way and that way. And so there's a phase shift, and it's shown here. And the beautiful thing about this formula, and the rotation rate is omega, is it's actually universal for, let's say, the non-relativistic heavy atoms going around versus the photons that might be in your rival Mach-Zehnder interferometer, your rival laser ring gyro. And you might say I have a pretty big advantage here, because the ratio of those two things, of the signal response, is almost 11 orders of magnitude. Time is brief and the subject is vast. This will continue later with this. This works extremely well. There's data here from Todd Gustafson's thesis from not quite 20 years ago. Here's another sales slide that describes how well atom interferometry does versus those evil competitors that are in the plane you fly in all the time. And again, we'll follow that in a later lecture. I want to conclude with a little bit of just the applications. Obviously, this was somewhat idiosyncratic discussion. Atomic clocks, and it's hard to read the slide over there, are now down using that basic Ramsey method or fancy variants of it, of getting frequency stabilizations to really a part in 10 to the 18 now, 10 to the 19. It's amazing. You can see the gravitational redshift placing the experiment on the floor versus on a table. And again, more about that later. I, again, described earlier, the atomic fountain gravity gradiometry works extremely well. We think we can do that in a passing vehicle. There are many applications to that. And then likewise, for future reference, the inertial motion sensors likewise are showing incredibly great promise. We recently, again, I was working closely with Dave, other people here, demonstrating, Stephen Bond and Jake Trueblood, demonstrating that this sensor really is a rival of GPS out in the field. So that's pretty cool. And then, again, this is more like you do in a seminar. I want to give credit. There's a large team of people that helped with this. And it's very important to point out we had 4 summer students who played a very big role here. And then finally, future talks. We're going to talk about the gyros, I promised, navigation, gravity tomography, GP there. I didn't get to talk about ADMX enough, but we should, dark matter detection, and also squeeze state subject, and a little bit about the signal analysis that goes into these things as well. So I should probably stop, but we're going to have fun in the future. So